thumbs up when you guys can share my screen.
Yep.
Okay, perfect. I'll keep the chat here so that we can answer any questions on the side. So let's get started. Maybe I'll start the first chapter and then I think I will nominate one of you to help me with the reading. So I think it will allow you to also improve the reading comprehension. Hope everyone had a nice Saturday. I'm just starting my Saturday. I'll probably just have some coffee and get started. So, chapter two. So, I think codes and combination. About chapter one. So, I think just summing it up very quickly, we learned about like if you have two friends, how you can talk to each other, how they discovered that Morse code is a very efficient way, how it works, and its significance in ham radio and Second World War and SOS and the other things. So, okay, yeah. So I think now we will go into a bit more technical stuff. And this is a cool thing about this book. I think it builds on something called first principles. I really love first principles. So first principle thinking is like whenever you see something super complex, how do you take it apart and make it like thin slices of it that allows you to see the basic working functionality of it, which is often not very complex. So let's get started. So, second chapter, codes and combination. So, Morse code was invented by Samuel Finley Breese Morse, 1791 to 1872, whom we shall meet more properly later in the book. The invention of Morse code goes hand in hand with the invention of the telegraph, which we will also examine in more detail. How many of you know Telegram with a raise of hand? I think most of you are fairly young, but have you ever received a telegram? Okay, I think Somava has, and that's all. I'm sure Sunny
I'm
knows.
assuming heard of, but I don't think have received. Maybe anybody would be there.
Oh yeah, nice. Okay, so yeah, I think it probably by the time we grew up, I think the telephones became a lot more common, but that used to be the way. Anyway, so yeah, so just as Morse code provides a good introduction to the nature of codes, the telegraph provides a good introduction to the hardware of the computer. You can think of it as the predecessor of this modern computing units you see. And it can go all the way back. I think while growing up, we all read, right? Abacus was the foundation of computer. Like you can take some very, very primitive tools and like you can see how eventually like humans love to build abstractions on top of things and then that's how we invent new things. So most people find Morse code easier to send than to receive. Even if you don't have Morse code memorized, you can simply use this table conveniently arranged in an alphabetical order. So I think we talked about this. There is also like a nice hack, like a guide that I shared, which shows you like how they derived Morse code. So receiving Morse code and translating it back into words is considerably harder and more time consuming than sending because you must work backwards to figure out the letter that corresponds to the particular coded sequence of dots and dashes. For example, if you receive dash dot dash dash, you have to scan through the table letter by letter before you finally discover that this code is Y. The problem is that we have a table that provides this translation in alphabetical letters to Morse code. So think of this as the last page as your modern day dictionary or a hash map. But the problem is there is no reverse hash map. So right now you're doing like brute force O of n. Like whenever you receive a code, you go through this whole table, all characters to find like what matches here, right? And you can see where we are going. But we don't have a table that lets us go backward. So that's like a reverse map that will allow us to do it in like O of 1 amortized time, where we can go from a Morse code to alphabetical letter. And you can see where this is going, right? Like there is a need. So first we find a problem, we solve the problem. We find that now there are two more problems, and then we figure out like how to solve them. So in early stages of learning Morse code, such a table would certainly be convenient, but it's not at all obvious on how we could construct it. There is nothing in those dots and dashes that can be put into alphabetical order. So how do you arrange them, right? Because we are still not talking programmatically. We are still talking organically, like where you will see from your eyes, your brain will be processing it, and then you need to figure out what it is. So So let's forget about the alphabetical order. Perhaps the better approach is to organize codes, might be to group them depending upon how many dots and dashes they have. So, for example, the Morse code sequence that contains either one dot or one dash can be represented by two letters, which are E and T. So, any Morse code that will have like at least one dot or one dash, it will either be a E or a T. And now a combination of exactly two dots or dashes gives us four more letters. So if I say, so these are the only letters which has like one single character. So a dot means E, a dash means T. And now we will say like, okay, what about the combination of two? So there are total four alphabets. That is a combination of like these two. And you can see this is a truth table, right? Like 00111001. So this is now dot dot dash dot dot dash and dash dash. So this is INAM. And then we say, okay, what about the pattern of three? So that gives us eight more letters. And you can see this is where this is going: 2 raised to the power 1, 2 raised to the power 2, and 2 raised to the power 3. So then this becomes 8. This is SURWDKGO. And finally, if you want to stop this exercise before dealing with numbers and punctuation marks, sequence of four dots and dashes gives us 16 more characters. So which is 2 to the power 4. And then these are the rest of the alphabets. So when taken together, these four tables contains 2 plus 4 plus 8 plus 16 codes for a total of 30 letters. And you can see there are a bit of an extra because there are some of these letter with some accent marks. This is because the four of the codes in the last table are for accented letters. I think they use it for Latin. 26 are used for Latin alphabets, but I think they are just there. We will learn why. So some of the languages use that. I have seen, I think French use a lot of accented letters. These four tables might help you translate with greater ease when someone is sending you Morse code. After you receive a code for a particular letter, you know how many dots and dashes it has, and you can at least go to the right table to look it up. Each table is organized so that you find all the dots in the upper left and the dash codes in the lower right. So this is also organized in a way that like you start with the, again, you can think of a dot as a 0 and a dash as a 1. So it starts with 0000, 0001, 0010. We are basically just adding one. It's a Boolean addition in a way, but that allows you to create like a key where you can look very quickly. So if I know there are three dashes, my eyes will automatically scan somewhere from here and will see, okay, it's this character. So can you see the pattern in the size of the four table? Like notice that each table has twice as many code in the table before it. This makes sense. Each table has the codes in the previous table followed by a dot and all the codes in the previous table followed by a dash. So this is like your standard permutation, right? Where if you have a sample space of 2, if you add one more thing, then one more space will basically have all the possible choices, and then you make like combinations of that. So we can summarize this trend in this way, like if there is just number of dots 1, so code is 2, 4, 8, 16. And each of the four tables has twice as many codes. So if the first table has 2, second table has 2 into 2, third table has 2 into 2 into 2, and there is another way of showing that. And then we can rewrite this as the powers, as we mentioned. So of course, once we have the number multiplied by itself, we can start using exponents to show power. For example, 2 into 2 into 2 into 2 can be written as 2 to the power 4, and 2, 4, 8, 16 are all powers of 2 because you can calculate them by multiplying by 2 itself. So our summary can be shown like this. So now this table has become very simple. The number of codes. Ankit, can you go on mute? Thank you. So this table has become very simple. The number of codes is simply 2 to the power of number of dots and dashes. So we might summarize the table data in this simple formula. Number of codes is equal to 2 raised to the power number of dots and dashes. And now you would realize that power of 2 tends to show up a lot in codes. We will see another example in the next chapter, but to make the process of decoding the Morse code even easier, we might want to draw something like this big tree-like table shown here. So now you can see like how the modern day data structures were slowly evolved as a process of us trying to solve things manually first. And this is the case with almost everything. Like when you think about object-oriented programming, I remember when I learned it, like we had this really nice teacher who would just tell us to look around the room and then think about how would you model this. Let's say I have this lamp here. How would you model this lamp in programming? Like what would be the base class, what would be the attributes, and then will there be elements that will it has some parent class or it will have some child class, like that. So so this is a very interesting table where you start with a simple dot and dash, and you can think, you can invert this in a way, and you can look at this as even a binary tree. So it starts with dot dash, and then you can either have a dot or have a dash. So it becomes, if dot dot becomes I, dot dash becomes A. Does anyone know what exactly do we call this data structure in programming? This is a very popular Google question, I think. So this is called a trie, TRIE. So trie is used. So let's see if we can find something. Trie data structure. Yeah, so it is used to store, it is used to basically break down a string into a tree. So if you see and, so it becomes A and B, and wherever the node eliminates, that becomes like that, that's where you can get the word. And then you can encode it. It basically compresses the data, because let's say if there was another word, an, then an can also be encoded as the same part. So now instead of using 2 plus 3 5 nodes to represent and, you compressed and you just share like some part of it that's there. So try is a beautiful, beautiful data structure. Like whenever you have questions about auto completion in Google, that happens, they are all based on like this. When I start typing like this thing, this is all powered from like very modern and very advanced versions of try. But at core, if you want to make something auto completion, you take your data set and you put it in a try, and then it allows you to, as soon as you type A, you know that you have these two choices. As soon as you type B, you know you have these two choices, like that. Okay, going back. Oh, by the way, if anyone has any questions, just raise hands and we will take that. So we are not going to just have some time at the end. So feel free to do that. Tree and trie data structures are not same. It's basically like all tries are trees in a way. So it's basically a derived form of that. A trie specializes in breaking down of a string into like a tree form, but a tree is usually can be represented to be represent anything. There are red black trees, there is binary trees, there is binary search trees, but you don't have to be binary, so you can have as many nodes as you want. So this table shows the letters that result from each particular consecutive sequence of dots and dashes. To decode a particular sequence, follow the arrows from left to right. For example, if you want to know which letter corresponds to dot dash dot, so we are maintaining an order where dot is on top and like dash is on bottom. So if I have to do dot dash dot, so I know dot dash dot, so I know it's an R, and the letter is R shown next to the last dot. If you think about it, constructing such a table was probably necessary for defining Morse code in first place. First, it ensures that you don't make the dumb mistake of using the same code for two different letters. And second, you are assured of using all the possible codes without making the sequence of dots and dashes unnecessarily long, right? Like imagine, like you can think, right? Like one another way that we discussed in the last chapter was that like you can use one blink for A, two blinks for B, three blinks for C, but that is not the most efficient way, because if I have to type something with a letter Z, I will have to do it 26 times. So, at the risk of extending this table beyond the limits of the printed page, we could continue it for the codes of 5 dots and dashes and more. A sequence of exactly 5 dots and dashes gives us 2 raised to the power 5 or 32 additional codes. Normally, that would be enough for 10 numbers and 16 punctuation symbols defined in Morse code. And now you can see there is a requirement to send numbers also. We just don't want to send alphabets, right? Like in the messages. So and defined, and indeed the numbers are encoded with 5 dots and dashes, but many of the other codes that use a sequence of 5 dots and dash represent accented letters rather than punctuation marks. To include all the punctuation marks, the system must be expanded to 6 dots and dashes. And now this is basically like it's a underlying bits that we are talking about, but we have not invented bits yet. So we are still talking like purely mathematically, because there is no computer, there is no hardware, and there is no concept of bits and bytes yet. Sachin, do you have a question?
No, no, it was just like waving hand, hello, wala.
Oh, hi, hey. So Okay, so to include all the punctuation marks, the system must be expanded to 6 dots and dashes, which now gives us 64 additional codes, which is 2 raised to the power 6. And that's an additional code. So the grand total, so make sure this is not inclusive, this is additive to like whatever we had. I'm hearing some disturbance. Okay. So now this is 2 plus 4 plus 8 plus 16 plus 32 plus 64. So this becomes 126 character. And this is now very close to what we talked. It's like a char set, right? Often, and this is a type of an encoding in a way. So that's overkill for the Morse code, which leaves many of these longer codes undefined. It's very similar to how we have these periodic tables where there are some higher atomic numbers and we don't know what to do it with yet, but then we find them and then we just put them there. So it's going to be a very similar journey. So the word undefined used in this context refers to a code that doesn't stand for anything. If you were receiving Morse code and you got an undefined code, you could be pretty sure that somebody made a mistake, because we were clever enough to develop this little formula, which is again this 2 raised to the power, like number of codes is equal to 2 raised to the power number of dots and dashes. So we could continue figuring out how many codes we get from using longer sequences of dots and dashes. And then you can see, like, if you use 10 dots and dashes to decode something, so then we have 1024 number of choices, and it keeps doubling and raising very fast. So fortunately, we don't have to write out all possible codes to determine how many there would be. All we have to do is multiply 2 by itself over and over again. Morse code is said to be a binary, literally meaning 2 by 2 code, because the components of code consist of only two things, a dot and a dash. That is similar to a coin, which can land on either head side or the tail side. Binary objects such as coins and binary codes such as Morse code are always described by power of 2. What we are doing by analyzing binary codes is a simple exercise in the branch of mathematics known as combinatorics or combinatorial analysis. Traditionally, combinatorial analysis is used most often in the fields of probability and statistics because it involves determining the number of ways that things like coin and dice can be combined. And we have all done that, right? Calculate the probability of two dices throwing how many times we will get a seven. So I think this it's like basically becomes fractional, but it also helps us understand how many codes can be put together and taken apart, right? So now this might also want you to help you ponder, like, I don't know how many of you did that. So like when I was growing up, I had this amazing pen with a light. So it had a UV light in the back and it was invisible ink pen. They were very popular and raged back day. And I remember, I think we had some friends and we used to call it the club of finer things, and we used to share notes with each other and we would write like things in codes. So the point of that saying that is that it's very easy to make a code as long as someone has a key to write it and someone has a key to decrypt it. And this is also a nod to how I think the handshakes work in real life. There is a concept of private key and public key, and we will probably get to that later in the chapters. Yeah, that was chapter 2. Any questions, comments? Okay, let's move on. So chapter 3, Braille and binary codes. So now we have built the foundation. We understand how where this concept of zeros and ones and binary comes from. So Samuel Morse was not the first person to successfully translate the letters of written language to an interpretable code, nor was he the first person to be remembered more as the name of his code than himself. Oh wait, sorry. I wanted someone else to read it. Like, who wants to nominate? And then I can help share the lores. Okay, Somava, you're up.
Okay. Yeah. So hmm, I should start with that honor must go.
You can start from the starting again if you want.
Okay.
Yeah.
Okay.
Mhm.
Samuel
One
Morse.
recommendation is don't read from Jatin's screen.
Okay.
Like,
Yeah.
if you're reading, then you can start sharing. We
Yeah,
can
sure.
share the link, right?
I have
This way
shared the
you're
link.
more in control. Yeah, just
Yeah,
in
on
case
chart.
he wants
I'll
it.
share it
Okay.
again. Yeah.
Yeah. Yeah. Yeah. I can do
Yeah,
that.
go ahead. Yeah, I'll stop sharing. You can share.
This way
Since
it's
it
more
was
clear. He
shared.
can zoom in where he wants to, etc. Yeah.
Yeah, makes sense.
Yeah. Okay.
Our concurrency has reached 35, Jatin.
Oh
We
wow,
started small, but yeah.
people are,
So,
yeah, that's nice.
Yeah. Is
Okay,
my screen
yes,
yes.
visible?
Yes,
yeah,
we
yeah,
can
you
see your
can
screen.
cross this bar. Oh yeah, this also works. Okay, go ahead.
Okay. Samuel Morse wasn't the first person to successfully translate the letters of written languages to an interpretable code. Not was he the first person to remembered more as the name of his code than as himself. The honor must go to blind French teenager born some 18 years after Samuel Morse, but who made his mark much more precisely. Little is known of his life, but what is known makes a compelling story. Louis Braille was born in 1809 in Copperet, France, just 25 miles east to Paris. His father was a harness maker. At the age of 3, an age when young boys shouldn't playing in their father's workshop, he accidentally stuck a pointed tool in his eye. The wound became infected and the infection spread to his other eye, leaving him totally blind. Normally, he would have been doomed to a life of the ignorance and poverty, as most blind people were in those days. But young Louis' intelligence and desire to learn were soon recognized through interventions of the village priest and school teacher. He first attended school in the village. Was the other children and the age of 10 was sent to Royal Institution for Blind Youth in Paris. One major obstacle in the education of the blind is, of course, there is inability to read printed books. Valentin Hoy, the founder of the Paris school, had invented a system of raised letters on papers that could be read by touch. But this system was very difficult to use, and only a few books had been produced using this method. The sighted Hugh was stuck in a paradigm to him, and a was and a was and and a and the letter A must look or feel like an A. If a given flashlight, if a given flashlight to communicate, he might have tried drawing letters in the air, as we did before we discovered it didn't work very well. Who probably didn't realize that the type of code quite different from printed alphabet might be more appropriate for sightless people. The origin of an alternative type of code came from an unexpected source. Charles Barbier, a captain of the French army, had by 1819 devised a system of writing he called Irrectune Nocturne or night writing. This system used a pattern of raised dots and dashes on a heavy paper and was intended for use by soldiers in passing notes to each other in the dark when quiet was necessary. The soldiers were able to poke these dots and dashes into the back of the paper using an awl like stylus. The raised dots could then be read with the fingers. The problem with the Barbier system is that it was quite complex. Rather than just patterns of dots and dashes that correspond to letters of this alphabet, Barbier devised patterns that correspond to sounds, often requiring many codes of single word. The system worked fine for short messages in the field, but was distinctly inadequate for longer texts, let alone entire books.
So just take a pause. So I think
Hmm.
you can see how now what we did is we solved the problem for visual like normal people, and then I think we thought about like how can we help visual impaired. But I think somebody mentioned in the last meeting that most of the technology we use comes from the war, and that's actually very accurate. The more you look
Hmm.
into it, so I think this is where also they are showing like how they basically did like a punch up. So punching is nothing but just like instead of punching a hole, we just like raise it so it becomes a bit more tactile, so that soldiers
Yes.
can feel it and pass notes in the dark.
Hmm.
Yeah. Okay, go on.
Louis Braille became familiar with the Barbier system at the age of 12. He liked the use of raised dots not only because it proved easy to read with the fingers, but also because it was easy to write. A student in the classroom, a student in the classroom equipped with the paper and a stylus could actually take notes and read them back. Louis Braille diligently tried to improve the system and within the 3 years, at age of 15, had come up with his own, the basis of which are still used today. For many years, the system was known only within the school, but it gradually made its way to the rest of the world. In 1835, Louis Braille contracted tuberculosis, which could eventually kill him shortly after his 43rd birthday in 1852. Today, enhanced version of the Braille system compete with the tape recorded books for providing the blind with access to written word, but Braille still remains in the invaluable system and the only way to read for people who are both blind and deaf. In recent years, Braille has become more familiar in the public arena as elevators and automatic teller machine are made more accessible to the blind. What we are going to do in this chapter is dissect Braille code and see how it works. We don't know how to actually learn Braille or memorize anything. We just want some insight into the nature of codes. In Braille, every symbol used in normal written language, specifically letters, numbers, and punctuation marks, is encoded as one or more raised dots within 2 by 3 cells. The dot of the cell commonly numbered 1 through 6.
So I think take a pause. So I think anyone has probably, I think you all have seen Braille in some form. I think if you go on a
In
metro
lefts.
station, in lifts, I think there are some places where it's now completely mandatory. And yeah, so I think this is, you can see, I think we are now going to talk about how this is also just a type of encoding. So all currency does not have proper Braille, as in like the same thing, Sumit, but currency has a markers that are raised which are distinct, that you can feel that. Maybe, but maybe I'm wrong, but that's what I feel, because in Indian currency I think there is like these shapes where there is a lotus behind 100 rupees, and behind 500 rupees there is something else that's there. But yeah, we'll see.
Yeah.
Go on. Yeah.
In modern day use, special typewriters or embossers punch the braille dots into the paper. Because embossing just a couple of pages of this book in braille would be prohibitively expensive, I have used a notion common for showing braille on the printed page. In this notations, all 6 dots in the cell are shown. Large dots indicate the part of the cell where paper is raised. Small dots indicate the part of the cell that are flat. For example, in the Braille character, dots 1, 3, and 5 are raised, and dot 2, 4, and 6 are not.
Just wait. Sachin, you had a hands up.
I typed it in the chat.
Oh, okay.
Or I can show it in my camera. Like these are the lines which are for blind people on a note. Like
Right.
these
But
Yeah.
this is
ones.
not Braille encoding, right?
This is not
Mm.
braille encoding. This is what
Yeah.
we have come up for recognizing. These are on both
Yeah.
sides. I opened the note and saw.
I also have a Indian note.
Like,
Yeah, you're right.
yes, yes.
Okay, go on.
Yeah. What should be interesting to us at this point is that the dots are binary. A particular dot is either flat or raised. That means we can apply what we have learned about Morse code and combination analysis to Braille. We know that there are 6 dots at that each dot can be either flat or raised. So the total number of combinations of 6 flat and raised dots is 2 into 2 into 2 into 2 into 2, or 2 to the power 6, or 64. Thus, the system of Braille is capable of representing 64 unique codes. Here they are, all 64 possible Braille codes.
So I think you can here also see it's very similar to Morse code in a way that there
Mm.
are these number of bits or choices, and then there is an on state or an off state, which is a dot or a dash or zero or a one. So in this case, it's flat versus raised.
Raised, yes. If we find fewer than 64 codes used in Braille, we should question why some of the 64 possible codes aren't being used. If we find more than 64 codes used in Braille, we should question either our sanity or fundamental truths of mathematics, such as 2 plus 2 equals 4. To begin discussing the code of Braille, let's look at the basic lowercase alphabets.
Yeah, so see, it's also following a very similar method. So like 00, so I think there is a dot in the top left, and then there is dot dot B, and then if it goes flat, it becomes C, then D, then E. So I think it probably will explain how this is constructed. But yeah, you can move on.
Yeah. Uh, for example, the phrase you and me in Braille looks like this. So notice that the cell of each letter within a word are separated by a little bit of space. A larger space, essentially a cell with no raised dots, is used between words. This is the basis of Braille as Louis Braille devised it, or at least as it applies to the letter of the Latin alphabet. Louis Braille also devised codes for letters with accent marks. Common in French, notice that there's no code for W, which isn't in classical French. Don't worry, the letter will show up eventually. At this point, only 25 of the 64 possible codes have been accounted for. Upon close examination, you will discover that the three rows of Braille illustrated adverb shows a pattern. The first row, letter A through I through J, uses only the top four spots in the cell, dots 1, 2, 4, and 5. The second row of duplicates the first row except that the dot 3 is also raised. The third row is the same except that dots 3 and 6 are raised. Since the days of Louis Braille, the Braille code has been expanded in various ways. Currently, the system used most often in published material in English is called Grade 2 Braille, and Grade 2 Braille use only contractions in order to save trees and to speed reading. For example, if letter code appears by themselves, they stand for common words. The following three rows, including completed and third row, shows these word codes.
So again, I think like any other, so also even about language. So why Latin keeps coming up? So I think most of the languages that use our modern day alphabets are derived from Latin. It's very similar how in India we say like most of the languages come from the Devanagari, right? So
Yes.
Devanagari is a script, Latin is a script that defines, and then people take it and modify it in their own way to create their own languages. But the root of that language, which is used to encode or construct words in sentences, is still like a nod to that cassette. So Latin is the cassette where they defined, and it's very cool to see how the words are formed. There are a couple of really nice videos on YouTube where you can see like how Latin words were formed. And
Mm.
again, you can keep going back in time and see like how it started, like what was the need, and like what were some of the elementary basic words at the start. And then this is, I think, a short form. So I think just like in English also, we have a lot of short forms that we use just to save time and compress the data so that we can be more efficient. That is same case with the Braille as well.
Yeah.
Yeah. Okay, go on.
Thus, the phrase you and me can be written in grade 2 Braille as this. So far, I have described 31 codes, the no raised dot space between words, and the 3 rows and 10 codes of letter for letters and words. We're still not close to the 64 codes that are theoretically available. In grade 2 Braille, as we shall see, nothing is wasted. First, we can use the codes for letter through J combined with a raised dot 6. These are used mostly for contractions of letter within the words and also include W and another word abbreviation. I think I'm spelling this not W. Is it a Greek letter?
I think they're still talking about the W alphabet. So if you see on the left, the UV, then W is missing, and then it's XYZ.
Okay.
So yeah.
For example, the word about can be written in grade 2 Braille this way. Second, we can take codes for letters through J and lower than to use only dots 2, 3, 5, and 6. These codes are used for some punctuation marks and contractions depending on context.
Mhm.
The first four of these codes are comma semicolon, colon, and period. Notice that the same code is used for both left and right parentheses, but that two different codes are used for open and closed question marks.
Quotation marks. Yeah. Okay.
Quotation
Let
marks.
me take over. I think I have to explain a couple of things also.
Mm.
So I'll start sharing if
Yeah,
you don't mind. Yeah.
yeah.
Let's keep this here and let's keep this here. I'm just arranging my windows. Nice. So Sachin has a question. Did we exhaust the entire 64 options available for this CAD set? No. So I think let me share. Give me a thumbs up if you can see my screen.
Yep.
Okay. I'll just reduce this to one line and then maybe we will put this here. Yeah. So no, so I think Sachin, what like we were talking about, I think these are six options, and what they have done is they have broken down the words. So if you go through A to J, they only use the top four spaces to keep it simple. So because when you're scanning with the hand, I think it's much more tactile to see. So if you ever see like someone reading Braille, they go like in this way. So like 1, 2, 3, 4, 5, 6 in that way. So I think then the third row is used for adding these things. But we have not exhausted this because there are a lot of other things that we are using it. So if you see CH, GH, so CH, this is like exclusive to that. So I think it is just a way to compress the words so that it can be more efficient to read tactile using your hand. So yeah, we are up to 51 codes by far. So I think we are keeping a count. So I think these were 26. Then there were a few more here, a few more here, a few more here, and then I think the following six codes use various unused combinations of dot 3, 4, 5, and 6 to represent contractions and some additional punctuations. So these are, I think, some of the words like like const, tent, like ing, like blee, ar, com. And the code for BLE is very important because when it's not part of the word, it means that codes that follow should be interpreted as numbers. So these number codes are same as letter A through J, which it is not a part of word. Oh, so I think they basically write blay, and this basically is the pound sign, which corresponds to the number. So I think whenever we have this, after that, whatever is there, this becomes like a number. So there is a sequence of this code where I think there is this first one is BLE, and then everything after that is a number. And then when we add a space, it resets back to being like A through J. So it's just like putting like a number to that. So if you have been keeping a track, we need now 7 more codes to reach the maximum of 64. So these are the left options that we have not done. The first one, arrays.4. So it's like 1, 2, 3, 4, 5, 6, like that. So the fourth dot is on the top right, is used as an accent indicator. The others are used as prefixes for some contractions and also for some other purpose. So when dot 4 and 6 are raised, the fifth code in this row, so here, the 1, 2, 3, 4, fifth, yeah, this one, sorry. Uh, yeah, the code is a decimal point in a number or an emphasis of indicator depending on the context. So I think this is basically just trying to ensure that the fidelity of a language is captured, right? So I think English is very English, or even Hindi. I think most of the modern day languages, they have space for including a lot of other things than your basic phonetic sounds, right? So like how do you speak brackets like parentheses? You cannot, but we need that to organize the data that we live in today. So there are a lot of words that they have no phonetic sound. Like if you look at your keyboard, all the symbols that you see, they have no phonetic sound, but they have a meaning either mathematically or by like a linguistic way. So similarly, if you are, and finally, if you are wondering how Braille encodes capital letters, right? Like we have a dot 6, the capital indicator. So think of this as your shift key or the caps lock key. This signals that the letter that follows is an uppercase. For example, we can write the name of the original creator of the system as, and I think there is this Braille. So this is the capital letter I and the contraction of OU. So you are breaking it. Instead of writing Jatin, let's say my name using this, I can take some of the contractions and use that. So for in, I don't need to do I and in. I can just directly use this in. And this is how you can just compress words so that it's much faster to write. And it's very similar to how, like, the blinking flashlight to the Morse code, we tried to compress the cat site so it's easy to pass the information. And then this one spells Braille. In the actual, the name might be abbreviated even more by eliminating the last two letters which are not pronounced. So it also follows, like, if you don't say it, you don't write it, again, to be more efficient. And I think we talked about the processing of information. We touched briefly in the last session, where there is a reason why image and now videos are very popular as a medium, because they get a lot more information across in a smaller span of time. So compared to a regular boring text, like if you are reading a text, it takes you a lot of time, but if you are hearing a text, someone speak it at like a much higher rate, your brain can still process it very quickly. So I think it's similar here, where you just try to eliminate it and like get as much information as you want. So in summary, we have seen how 6 binary elements, the dots, yield 64 possible codes and no more. It just so happens that many of these 64 codes perform double duty depending on their context. Of particular interest is the number indicator and the letter indicator that undoes the number indicator. So it's basically like your tags, where you like in your code you start a parenthesis, you end it, and then that's the context that is there for that. It's a very similar thing. So these codes alter the meaning of codes that follow them, from letters to numbers and from numbers back to letter. Codes such as these are often called precedence or shift. And now you can see like where the shift key in your modern day typewriters and modern day computers came to be. Like they all just build on top of like some of the things that existed. So they alter the meaning of the subsequent code until the shift is undone. The capital indicator means that the following letter and only the following letter should be uppercase rather than lowercase. A code such as this is known as the escape code. And again, I think if you are a modern day software engineer, you can understand that how we need to escape certain characters when we are putting them in a string. Like this is how the origin of this terminology comes to be, right? Like if you have a string in URL and you just put like an ampersand or a percentage sign, you always have to escape them so that they are interpreted as like that. So escape code lets you escape from the humdrum routine interpretation of a sequence of code and move to a new interpretation. As we will see in the later chapters, the shift code and the escape codes are common when written languages are represented by binary codes. So that was our chapter 3, a pretty heavy chapter in a way. Any questions or comments?
Okay, interesting. I mean, originally I did not have a lot of idea of what the book was going to cover, but I now
Yeah.
see the sense of, all right, we're talking about how codes came about, and even before computers, where did we originate doing codes, even without the need for binaries and all of those things. Real world use cases forced us to create codes much before
Yeah.
computers ever came around. Yeah,
Yeah, exactly.
interesting.
So I think it just builds on that. And it's very funny. I think some of the people who will be born today, whenever they save something in a GUI, they click a floppy button without ever knowing what that floppy is, right? Like there is that save button. So I think it's just that there is a lot of legacy things. I think the more you read, the more dots you can connect across. And that is, I think, as I mentioned in the first meeting, also the beauty of reading. So when you read something completely new, which you will probably never come across in your general algorithm driven social network, it allows you to think and make these connections really well. Yeah, Sachin is right. I think developing a different meaning of code. Exactly. I think it's again, a code is basically a representation to get your message across. I think Izumi has a question. So just joined today. Just a quick question. Should I read the previous chapter? Yeah, you can read the previous chapter. So this is going to build on each chapter will build on top of another chapter. So I think before next session, I would recommend you to go through that. We are also recording these videos. We have to figure out a cadence on publishing them. So we will see. But we first want to go through some chapters before we start publishing, so that like we are a little ahead of the publishing schedule. So let's talk about chapter 4. Uh, So, Somava has a question. Does the keyboard button codes came from the idea of Braille? Not exactly Braille, but I think probably we will talk about that. But like, if you have to, again, first principle thinking, if you have to break it down, before keyboard there was a typewriter, and before typewriter, how would you print a word? So there used to be this Gutenberg press, where I think they will have these big metal letters, and they will arrange these letters in a plate. They will put like an ink pad, they will punch it, get the ink, remove it, put a paper and punch it to get that across. So you can think of that a typewriter as a miniature form of a Gutenberg press. Basically, you had your own press where if you press a letter, it will go and punch. Like there would be a metal rod with the letter shaped embossed at the end. And whenever it goes back, it rests on like a ink pad. They call it like a tape. I forgot. There is some typewriter tape, but that tape has ink. So whenever it goes, it just goes and punch on a paper. So a lot of these things that we have around are basically miniature versions of the things that we started with. Like if you think of the original engine that James Watt built, it was huge, it was massive. And now if you look at your scooty, Activa, or like a bike, a 100cc bike, like we have such small engines which are so efficient in burning fuel and converting that fuel into torque like that. Sachin has a comment. I wish to know how fast can a good braille reader get? Can it compete with visual input? That's a good question. I don't know. Why don't you find that out and let us know? Like what is the speed? I think a human can probably read 80 to 100 words per minute. But if you hear them, you can probably go even further, like 150 to 180 words per minute. Like if you listen to a podcast at 1.5x, you can still make out like what they are talking about. So yeah, maybe you should check that out. Let us know, Sachin. So, chapter 4, anatomy of a flashlight. So, flashlights are useful for numerous tasks, of which reading under the covers and sending coded messages are only two most obvious. The common household flashlight can also take center stage in an educational show and tell of magical stuff known as electricity. Electricity is an amazing phenomenon, managing to be pervasively useful while remaining largely mysterious, even to the people who pretend to know how it works. But I'm afraid we must wrestle with electricity anyway. Fortunately, we need to understand only a few basic concepts to comprehend how it is used inside computers. The flashlight, and I think this is a popular joke. Somebody was writing like ChatGPT is a rapper on Transformers is a rapper, and I think all the way down, I think it goes down to electricity. I think that just powers everything, and you can probably keep going down into, I think, breaking down it further. Only if we could see under an electron, but we cannot today. So the flashlight is certainly one of the simpler electrical appliances found in most homes. Disassemble a typical flashlight, and you will find it consists of a couple of batteries, a bulb, a switch, and some metal pieces, and a plastic case to hold everything together. You can make your own no frills flashlight by disposing of everything except the battery and the light bulb at the end of the day. You don't really need anything else. You will also need some short pieces of insulated wire with the insulation stripped from the ends and enough hands to hold everything together. So basically, like you have a battery, you will probably need two wires. Either you solder it or you clip it, and then they just need to go to the two terminals of the bulb. Oh, they have shown that diagram here. And notice the two loose ends of the wire on the right side of the diagram. That's our switch, the classic. And that's why switch looks like that in physics, like when you draw that. Assuming that the batteries are good and the bulb is not burnt out, touching those two loose ends together will turn on the light because the circuit will complete. What we constructed here is a simple electrical circuit. And the first thing to notice is that a circuit is a circle or a loop, like in a way. The light bulb will be lit only if the path from these batteries to the wire to the bulb to the switch and back to the batteries is continuous. Any break in this circuit will cause the bulb to go out. The purpose of the switch is to control this process. The circular nature of the electrical circuit suggests that something is moving around the circuit, perhaps like water flowing through the pipes. The water and the pipe analogy is quite common in explanation of how electricity works, but eventually it breaks down as all analogies must. Electricity is like nothing else in this universe, and we must confront on its own terms. The prevailing scientific wisdom regarding the workings of electricity is called the electron theory, which says that electricity derives from the movement of electrons. I think that's what we all grew up studying, right? That there is a flow of electrons that goes from the negative terminal to the positive terminal. As we know, all matter, the stuff that we can see and feel, usually is made up of extremely small things called atoms. Every atom is composed of three types of particles. They're called neutron, protons, and electrons. You can picture an atom like as a little solar system with the neutrons and protons bound into the nucleus and the electrons spinning around the nucleus like the planets around the sun. Does anyone remember the name of the scientist that came up with this model, the model of the atom? No, Neil Bohr. I remember it. I think there was a Thomson, J. J. Thomson model, which was basically like a pie. I remember it very well because my teacher was so amazing. I was in a DAV school. So chemistry teacher, she actually baked legendary woman. She baked a pie and bring it to the school, and that had like minus and plus gems on it. So that was like the J. J. Thomson model. And then the Neil Bohr came and said like, oh no, it seems like the neutron and protons are together. And then there are electrons that go around the loop. Okay. I should mention that this is exactly what you would see if you were able to get a microscope powerful enough to see an actual atom, but it works as a convenient model. Yeah, so I think after that, so it doesn't exactly look like that, but this is a close enough representation to explain what it is. Yeah, the plum pudding model, Sachin. Yes. So the atom shown on the preceding page has 3 electrons, 3 protons, and 4 neutrons. So you can even count that. This is a black and white book, but I'm sure like there is some differentiation between the nucleus, which means that the atom. This is an atom of a lithium. So lithium is one of the 112. Now I think we have a lot more. Let's see how many elements in periodic table. 118. So we keep finding more, as I say, but there are still like a lot of unknown places in the periodic table. Okay, so yeah, so I think this is a atom of lithium. Lithium is one of the 118 now known elements, each of which has a particular atomic number ranging from 1 to 112. The atomic number is of an element indicates the number of protons in the nucleus of each element atoms, and usually also the number of electrons in each atom. And this is where the concept of ions comes in, where like if your atom gains an electron, it gets positively charged, or it gets negatively charged. If it loses an electron, it gets positively charged, and that's actually important for understanding how this works. So the atomic number of lithium is 3. The atoms can chemically combine with other atoms to form molecules. I think that's what we studied in the chemistry. So molecules usually have very different properties from atoms. They comprise. For example, water is composed of molecules that consists of 2 atoms of hydrogen and 1 atom of oxygen, like hence H2O. Obviously, water is appreciably different from either hydrogen or oxygen. So basically, we are talking about the physical properties. Like hydrogen and oxygen both exist as gas in their natural form, but H2O is usually a liquid. So likewise, the molecules of table salt consist of atom of sodium and a sodium atom of chlorine, so NaCl, sodium chloride. Neither of which should be particularly appetizing on French fries. So if you directly put sodium, don't do it. Don't eat sodium; it's poisonous. But if you take anything in or chlorine, like if you see like when a swimming pool is recently cleaned, it smells really bad, and that is the smell of chlorine. Uh, but salt is amazing. We put salt on everything. So in this way, like hydrogen, sodium, oxygen, and chlorine are all elements. Water and salt are called compounds. Salt water, however, is a mixture rather than a compound because water and salt maintain their own properties. Even if it looks like it's diluted, it's more like suspended really well in each other. The number of electrons in an atom is usually the same as number of protons, but in certain circumstances, the electrons can be dislodged from atoms. That's how electricity happens. So in the Neil Bohr model, I think it did not have just one orbit. I remember it had multiple orbits. And I think we learned that how electrons can jump across the orbits. So word electron and electricity both derive from ancient Greek word electron, which you might expect means something like tiny invisible thing, but no. Electron is actually the Greek word for amber, which is the glass-like hardened sap of trees. So I think it's probably that juice that oozes out of like some of the trees. The reason for this unlikely derivation is that ancient Greeks experimented with rubbing amber with wool, which produces something we now call static electricity. And I think every one of you probably has experienced static electricity, especially in winters when you take off a sweater after a long day, or like a woolen jacket. Or I think even as simple as just blowing up a balloon and like rubbing it on your hair, and then you can just put it on the wall and sticks. It uses like static because it gets statically charged. So the protons and uh, yeah, rubbing wool on amber causes the wool to pick up electrons from the amber. The wool winds up with more electrons than protons, and the amber ends with fewer electrons than protons. In modern experiments, carpeting picks up electrons from sole of our shoes. Protons and electrons have a characteristic called charge. So protons are said to have a positive charge, and electrons are said to have a negative charge. Neutrons are neutral and have no charge. Does anyone know now what is inside a neutron? I think we now know actually. We did not know. Yes, quarks, and I think there is another element. Something with glue. I forgot. So quarks and leptons. Oh, gluons and leptons. Yeah. So I think we have been able to slice apart a neutron and see what's inside it. So it's pretty fascinating. It was not a thing when I was in a school, but now it is. So even though we use plus and minus sign to denote protons and electrons, the symbols don't mean plus and minus in arithmetic sense, or the protons have something that electrons don't. The use of this symbol just means that protons and electrons are opposite in some way. The opposite characteristics manifest itself in how protons and electrons relate to each other. Protons and electrons are the happiest and the most stable when they exist together in equal number. So you can think of it like if there is three protons and three electrons, it just cancels out in a way in terms of the charge. An imbalance of proton electron will attempt to correct itself. When the carpet picks up electron from your shoes, eventually everything gets evened out when you touch something and feel a spark. That spark of static electricity is the movement of electrons by a rather circuitous route through the carpet, through your body, and back to your shoes. Another way to describe the relationship between protons and electrons is to note that opposite charge attracts like charge repel. And we all know that. We have seen that in multiple places. And this is a theory that goes in a lot of places. So even if you look at magnet, I think they have like a poles, like North Pole, South Pole, or positively charged or negatively charged, and then they repel each other. The protons are held together by something stronger than repulsion of like charges, and that is something called the strong force. It had a name also for it. I'm forgetting right now, but yeah. Messing around with the strong force involves splitting the nucleus, which produces nuclear energy. In this chapter, we are merely fooling around with the electrons to get electricity. And you all probably have read fission and fusion, and I think fusion is probably much more difficult than fission, it's the other way around. Yeah, but I think we can split an atom and it generates like tremendous amount of energy, and we still don't understand it why it happens. We know how it happens, but yeah. Static electricity isn't limited to the little sparks produced by your finger touching doorknobs. During storms, the bottom of the cloud accumulate electrons while the top of the clouds lose electrons. Eventually, the imbalance is evened out with a stroke of lightning, like when it just like goes and hits the atmosphere. Lightning is a lot of electrons moving very quickly from one spot to another. The electricity in a flashlight circuit is obviously much better mannered than a spark or a lightning bolt. The light burns steadily and continuously because the electrons are not jumping from one place to another. As one atom in the circuit loses an electron to another atom nearby, it grabs another electron from adjacent atom, which grabs an electron from another adjacent atom, and so on. So you can see it's like a chain reaction going on. The electricity in a circuit is the passage of electron from atom to atom. So like when you see a copper wire and you put like a charge on it, there it's basically like some electrons that are jumping across. This does not happen by itself. We cannot just wire up old bunch stuff and expect some electricity to happen. We need something to precipitate the movement of electrons around the circuit. So that's what where we say that it needs to have some potential, and that's where the concept of volt comes into the picture. But I think maybe they will explain that. So looking back at our diagram of no frills flashlight, we can safely assume that the thing that begins the movement of electricity is not the wire and not the light bulb. It's probably the batteries. Almost everyone knows a few things about the type of batteries used in flashlight. They are in tubular in shape, like cylinders, comes in different size. There is DC, A, AA, AAA. AA and AAA are the most common ones. Regardless of the battery size, they're all labeled as 1.5 volts. Not all, honestly, there are different voltages also, but most batteries are 1.5 volts. One end of the battery is flat and is labeled with a minus sign. The other end has a little protrusion and is labeled as a plus sign. If you want your appliance to work right, it's a good idea to install the battery correctly with the plus sign facing the right way. All of you know that. Batteries wear out eventually. Sometimes they can be recharged and sometimes they cannot be done that. And finally, we suspect in weird way that battery produces electricity. We all know that. We are actually out of time. Let me see how many pages. So we have 4 more pages. Are you guys okay to stay on the call, or should we continue it next week? Okay.
I'm fine. Anybody not okay, just comment. We'll take about 10 more minutes, maybe.
Yeah, probably less than 10. Yeah.
Yeah.
So okay. So in all batteries, chemical reactions take place, which means that some molecules break down into other molecules, or the molecules combine to form new molecules. The chemical in battery are chosen so that the reaction between them generates pair electrons on the side of battery marked with a minus sign, called the negative terminal or an anode, and demand extra electrons on the other side of the battery. That is called a positive terminal or a cathode. In this way, a chemical energy is converted into electrical energy. So basically, in a very simple words, let's see. I 3D printed this battery thing, but if you look at a cell, I think this cell has a need where I think there is a potential difference, and that is basically the volt, right? If you remember that Ohm's law and everything. So there is a potential difference between negative terminal and positive terminal, and if I connect both of them with the wire, the electrons will flow from negative to positive, and it will keep happening until both the sides have equal electron or an equilibrium has been reached. And this is a rechargeable cell. So what happens is, like, when I put this into one of the chargers, which I don't know where it is, it basically uses the electricity from my wall to again move a number of electrons to go back and go on the negative side, so that there can be a potential difference of 1.5 volt that can be created. So if you have a multimeter at home, and if you see a battery that doesn't work, it doesn't mean that it has now 0 volts. It will never be that case, because it's like a very declining kind of a graph. So if you put a multimeter, a new battery will show 1.5 volts, but a battery that doesn't work anymore will probably be 1.3 or 1.2 volts. So that's why, like, I think in middle class families in India, like I come from one, so whenever, like, I used to have this hand game. Whenever the cells will not work in my game, my mother will take it and put it in a clock, because that does not require like the full 1.5 volt, and it has like less load, so it still works. Keep this back. Anyways, going back. So the chemical reaction cannot process unless there is some way that the extra electrons can be taken away from the negative terminal of the battery and delivered back to the positive terminal. So if the battery is not connected to anything, nothing happens. It's stable. Because I think there is a word I forgot, but there is something that separates, I think, the both the things. And if you open up a battery, I don't recommend you to do. It's very dangerous. But if you see the videos and if you open it, it's basically there are 2 layers, and these layers are separated by insulated material. And it's the same thing. One layer is positively charged and one is negatively charged. Please don't open a battery. But so if the battery is not connected, nothing happens, but very slowly. The reactions take place only if an electrical circuit is present to take the electrons away from the negative side and supply electrons to the positive side. And electrons travel in this circuit around the clockwise direction. So it goes from negative to positive. In this book, the color red is used. We have a black and white book, but the color red is used to indicate that electricity is flowing through the wires. The electrons from the chemical in these batteries might not so freely mingle with the electrons in the copper wire, if not for a simple fact: all electrons, wherever they are found, are identical. So basically, they are very homogeneous in nature. There is nothing that distinguishes a copper electron from any other electron. Anyone knows why copper is a good conductor of electricity? Why do we use copper? You would have thought about this.
वैलेंस इलेक्ट्रॉन की बात कर रहे हो?
Sorry?
It has a valence electron in its outermost, more like
Yes,
most
well,
metals. Yeah.
right. Yeah. So yeah, most metals, but copper has an interesting property where the it has like a lot of what do we call it? Like orbits, but there was a scientific word for it. But the electrons in outermost orbit are not held with a lot of force, so they are much easier to jump across to the adjacent atom, and it has two free electrons, as Sudarshan also said. So it conducts electricity like really nicely. But again, it's a question of potential, right? There is that diodes, right? If you remember NP diodes, there is a certain level after, like if you provide high enough volt, most metals will become conductive. It's a question of like how much voltage you are giving. Even not just metals, like if you take a piece of wood and put like a negative and a positive terminal, like nothing will happen for a while. But if you keep increasing the volt, you will see that electricity will soon find its way through the moisture in the wood and will create its own circuit. There are some really good experiments on YouTube on that. But yeah, air will also conduct it. So Tesla coil is a really good example. So where he gave a proposal that electricity can travel wirelessly. Okay, so notice that both batteries are facing the same direction. The positive end of the bottom battery takes electron from the negative end of the top battery, and it's as if the two batteries have been combined into one bigger battery, with the positive terminal at one end and negative terminal at other end. The combined battery is 3 volt rather than 1.5 volt, and that is because they are put in a series. So whenever you put a power source in series, it adds. If you put it in parallel, it just stays the same. If we turn one of these batteries upside down, the circuit won't work. The two positive ends of batteries need electrons for the chemical reaction, but there is no way electrons can get to them because they are attached to each other. If the two positive ends of batteries are connected, the two negative ends should also be connected. So here, so this works. The batteries are said to be, I'm just running ahead of the book, but yeah, are said to be connected in parallel rather than in series as shown earlier. The combined voltage is 1.5 volts, which is same as the voltage of each of the battery. The light will probably still glow, but not as brightly with two batteries in the series. But the batteries will last twice as long. So it's basically inversely proportional to how you are consuming that. We normally like to think of a battery providing electricity to a circuit, but we have seen that we can also think of a circuit as providing a way for the battery chemical reactions to take place. The circuit takes electrons away from the negative end of the battery and delivers them to the positive end of the battery. The reaction in the battery proceeds until all the chemicals are exhausted, at which time you throw away the battery or recharge it. So from the negative end of the battery to the positive end of the battery, the electrons flow through wire and light bulbs. But why do we need the wires? Cannot electricity just float through the air? I think what just Sachin said. Well, yes and no. Electricity can flow through air, particularly wet air or humid air, or else we wouldn't see lightning. So lightning is basically, if you see like electricity traveling through your atmosphere, and sometimes it makes contacts to the ground, like when the voltage is very high. And that's why I think on the tall buildings you would have seen they have this giant metal rod. The whole idea is that again, electricity likes to find the path of least resistance. So if it is going around the atmosphere and if it sees a metal object, it will instantly go to that to neutralize. And that's why they say like whenever working with like wires and all, you should always wear like rubber slippers or something so that there is an insulator. Because if you get in touch with let's say like electricity on my finger, and if my feet are connected to the ground, it will try to find its way through my body. Sometimes it will not go through the heart or some major organs, and sometimes it will, but when it does, it will really mess it up. So, oops, sorry. So some substances are significantly better than others for carrying electricity. The ability of an element to carry electricity is related to its subatomic structure. Electrons orbit the nucleus in various levels called shells. Yeah, that's what I was trying to recall. An atom that has just one electron in its outer shell can readily give up that electron, which is what is necessary to carry electricity. These substances are conductive to carrying electricity and thus are said to be conductors. The best conductors are copper, silver, and gold. It's no coincidence that these elements are found in the same column of periodic table. Copper is the most common substance for making wires. The opposite of conductance is resistance. So some substances are more resistant to the passage of electricity than others, and these are known as resistors. If a substance has a very high resistance, meaning that it doesn't conduct electricity much at all, it is known as insulator. Rubber and plastic are good insulators, which is why these substances are often used to uh, which is why these substances are often used to coat the wires. So if you see like all your insulation of a wire, it's like a interesting rubber mix that we cut across. But even like giant wires with 440 volts, like they have such big insulation that you can just hold them and not feel anything at all. So cloth and wood are also good insulators as dry air. Just about anything will conduct electricity, however, if voltage is high enough. Copper has a very low resistance, but it still has some resistance. Everything has a resistance. And that's where I think the whole concept of potential comes into the picture. Uh, the longer the wire, the higher resistance it has. If you tried wiring a flashlight with wires that were miles long, the resistance in wires would be so high that the flashlight would not work. The thicker the wire, the lower the resistance it has. Maybe somewhat counterintuitive. You might imagine that a thick wire requires much more electricity to fill it up. But actually, the thickness of wire makes available many more electrons to move through the wire. I have mentioned voltage but haven't defined it. What does it mean when battery has 1.5 volts? Does anyone remember Ohm's law? Voltage is equal to, yeah, V is equal to IR. What is I and what is R?
Current and resistance.
Yeah. So voltage is current into resistance. Exactly. So actually, the voltage name after Count Alessandro Volta, who invented the first battery in 1800s, is one of the more difficult concepts of elementary electricity. And batteries used to be also huge. I think the like I don't know if you guys in school did that experiment where you can create a battery using two beakers of a positively and a negatively charged ion, put metal rods, and then you can power a light bulb. We did that, but they used to be pretty big, and now I think it is even this is pretty big from today's standard. Like now that we have button cells that gives us like consistent 1.2 volts. There is one running in your probably motherboard of this computer if you're connected through as well. So voltage refers to the potential of doing work. Voltage exists whether or not something is hooked up to a battery. Consider a brick sitting on a floor. The brick has very little potential, and they're all concepts that like are intermingled with each other. Held it in your hand 4 feet above the floor, the brick has more potential, right? We say there is a potential energy, there is a kinetic energy, and energy is neither created nor destroyed; it's only transformed. So it's funny because when I lift the brick, I'm spending some of my physical energy to add potential to that brick. In all three cases, and now held it in your hand at the top of a building, the brick has much more potential. In all three cases, you're holding the brick and not doing anything, but the potential is different, right? Like if I throw a brick from 4 feet versus if I throw it from 100 feet, the impact would be much different. It will have a lot more energy and a lot more impact. So, a much easier concept in electricity is the notion of current. The current is related to the number of electrons actually zipping through the circuit. Current is measured in amperes, named after Andre Marie Ampere. But everyone called them amps, as in a 10 amp fuse. To get 1 amp of current, you need about, let's see, if I know this, like 1,000, million, billion, trillion. What is after trillion? Quadrillion? Yeah. So probably 6240 quadrillion electrons flowing past a particular point per second. The water and pipe analogy helps out here. Current is similar to the amount of water rushing through a pipe. And voltage is similar to the water pressure. Oh, that's actually a really good one. And resistance is similar to the width of a pipe. The smaller the pipe, the larger the resistance, right? So when we wash the car, if you don't have that those fancy thing, you just squeeze the end of the pipe, and then like you can you get like a much better pressure. And these are like some variables that you can tweak with. So either you can have a tap that has a very high pressure, or you can have a pipe that is very small. So like you can change those things. So the more water pressure you have, the more water flows through the pipe. The smaller the pipe, the less water that flows through it. The amount of water flowing through a pipe or current is directly proportional to the water pressure, the voltage, and inversely proportional to the skinniness of the pipe, the resistance. In electricity, you can calculate how much current is flowing through a circuit if you know the voltage and the resistance. Resistance is the tendency of substance to impede the flow of electrons, is measured in ohms, named after Greg Simon Ohm, who also proposed the famous Ohm's law. This law states that I is equal to E by R, where I is traditionally used to represent current in amperes, E is used to represent voltage. Now we say V by R in modern science, electromotive force, and R is resistance. For example, let's look at the battery that is sitting around, not connected to anything. The voltage E is 1.5. That is its potential of doing work. But because the positive and negative terminals are connected solely by air, the resistance is very, very high, which means that the current I equals 1.5 volts divided by a very large number, which means that the current is almost about zero. The denominator is huge. Now let's connect the positive and negative terminal with a short piece of copper wire, and from here on, the insulation of the wires won't be shown. This is known as a short circuit. The voltage is still 1.5, but the resistance is now very, very low. The current is 1.5 volt divided by a very small number. This means that the current will be very, very high. Lots and lots of electrons will be flowing through the wire. In reality, the actual current will not be limited by the physical size of the battery. The battery will probably not be able to deliver such a high current, and the voltage will drop below 1.5 volts. If the battery is big enough, the wire will get hot. And again, this is something you can see. So this is a smaller battery, but there is that double battery, right, that we put in, I think, our bike horn or something. The 3 volt battery. If you connect it with a very thin wire, it becomes like red hot. It actually becomes fairly hot. You can actually start a fire with it. And a lot of people who travel a lot and camp a lot, they carry it in their pouch, because if you have steel wool, you can use that to create sparks and lit up fire. Anyways, so if the wire will go hot, it will actually glow and might even melt. And that's basically the concept of bulb, right? Like when Edison discovered it, it's basically he found a metal that will glow without melting at a certain voltage. But we'll probably talk about that. Most circuits are somewhere between two extremes. We can symbolize them like so. So the squiggly line here is recognizable to electrical engineers as a symbol for a resistor. Here it means that the circuit has a resistance that is neither very low nor very high. If a wire has low resistance, it can get hot and start to glow. This is how oh yeah, they're talking about it. Incandescent light bulb works. The light bulb is commonly credited to one of the most famous inventors, Thomas Alva Edison. And it's fairly new. You see, it's not even been 100 years since he's died. Like some of the things we think they are very ancient, but I think when you are on an exponential growth, it seems like you're on a linear path, but you need to zoom out further to see that it's actually exponential. But the concepts were well known at the time he patented the light bulb in 1879, and many other inventors also worked on the problem. Inside a light bulb is a thin wire called filament, which is commonly made of tungsten. Tungsten is one of the metals elements. One end of a filament is connected to the tip of bottom of the base, and the other end of filament is connected to the other side of the metal base, separated from the tip by an insulator. The resistance of wires caused it to heat up. In open air, the tungsten would get hot enough to burn, but in vacuum of a light bulb, the tungsten glows and gives off light. And now I think they put nitrogen, they put something in the bulb. I don't remember, but yeah. Most common flashlights have two batteries connected in series. A total voltage is 3 volt. A light bulb of a type commonly used in a flashlight has a resistance of about 4 ohms. Thus, the current 3 volt is divided by 4 ohms, or 0.75 ampere, which can also be expressed as 750 milliamperes as a metric system. This means that 4680 quadrillion electrons are flowing through the light bulb every second. A brief reality check: if you actually try to measure the resistance of a flashlight bulb with an ohm meter, so if you have a multimeter, it even has a setting where you can move it to resistance. And it's very cool. You can go around the house trying to find resistance of multiple things. If you don't have a multimeter, it's 300-400 rupees. Get it from Amazon, one of the best things you will buy. I almost use it like every week or something around the house. But you will get a reading much lower than 4 ohms. The resistance of tungsten is dependent upon its temperature. The resistance gets higher as the bulb heats up. As you may know, the light bulbs you buy from your home are labeled with a certain wattage. And not just your light bulb. I think everything has this watt hour rating. Your batteries of your phone, like this MacBook I have, has a 95 watt hour battery. It basically just means like how much potential it has, or power. Watt is a symbol of power. So Watt is named after James Watt, who is best known for his work on steam engine. The watt is a measurement of power and can be calculated as E into I, or V into I, voltage into current. The 3 volts and 0.75 amp of our flashlight indicates that we are dealing with a 2.25 watt light bulb. And I think in India they say there is a 0 watt bulb. I don't know if you have heard. There is no such thing as a 0 watt bulb, but the whole idea is that it is such a low watt bulb that it takes very less amount. And it's a thing, if you go and buy like a 50 watt or a 100 watt bulb, and if you screw it in, it gets like very hot. Like you cannot touch it once it's light up, and you have to wait for it to cool down. Your home might be lit by a 100 watt light bulb. Those are designed for 120 volts. So this is an American book. In India, we use 220 volts and 50 hertz, 60 hertz. How many hertz do we use in India? 50, 60?
60, 60 is what we do. 50 is what uh,
US does, I think. Yeah.
appliance supports. Yeah.
Oh, yeah. Oh, no, it's used 50 actually.
50, 60, both work for us. Like,
Oh, right,
I
right,
think
right,
most electronic appliances these days support
Support
both.
both.
Yeah, they
Yeah.
switch.
Right. In US, I think this is 120 volt. So this is why like half of the things I got, they don't directly work. If they don't have a built-in power supply, like,
Hmm.
and have something that only works at 220, it won't work for 120 volts. So thus the current that flows through them is equal to 100 watts divided by 120 volts, or about 0.83 ampere. Hence the resistance of a 100 watt light bulb is 120 volts divided by 0.83 ampere, or 144 ohms. So we have seemingly analyzed everything about the flashlight, the batteries, the wires, and the light bulb, but we have forgotten the most important part. Yes, the switch. The switch controls whether electricity is flowing in a circuit or not. When a switch allows electricity to flow, it is said to be on or closed. An off or open switch does not allow electricity to flow. The way we use the words closed and open for switch is opposite to the way we use them for a door. A closed door prevents anything from passing through. A closed switch is allows electricity to flow. Either the switch is closed or it's open. Seems like there is a typo here. Switched. Either current flows or it doesn't. Either the light bulb lights up or it doesn't. You can see again, it's very binary in nature. It's either one or it's either zero. Like the binary codes invented by Morse and Braille, this simple flashlight is either on or off. There is no in between. The similarity between binary codes and simple electrical circuit is going to prove very useful in chapters ahead. And if you know where this is going, you will understand why we spent last 30 minutes talking about electricity. Because if you again go back to your education around 9th, 10th, I don't know how the curriculum is these days. We started with these gates, and or not, XOR, and then using those gates, we built those half adder and full adder, which were basically some logical circuits. And then we built on top of that even further. Uh, so yeah, I think that was chapter 4. I think we made some really good progress today. I can give 2 minutes if anyone has any questions. Happy to take that. But I hope you
I
guys
have
enjoyed. It was like
posted a
a, yeah.
I have posted a tweet link that if we get a repost on, we may get more people to join in as well.
Perfect. And I see you have also shared a link to a multimeter. So get it. It's pretty
Yeah.
cheap actually, 242 rupees. It's you can go around the house putting it in everywhere. Don't just shock yourself. I take no liability of that. But any
Yeah.
questions? Okay, Dave has a question, I think. Or I don't know if he's saying he has a multimeter. Okay.
It's pretty open-ended.
You're on mute somehow. If you were saying something. Oh, all good. I don't think anyone has any question. Cool, guys. Thank you so much. Hope you guys enjoyed it, and I'll see you next week.
Thank you, Jatin. Thank you,
Yeah,
everybody.
absolutely. Bye bye.